Hello everyone, I am Shreyansh Kumar and I am here along with my teammates Aarush Nair and Tanishq Patil to present our topic shift registers, counters and their applications. Now, before we begin, let me set a small context. In the world of digital electronics, almost every system, whether it's our calculator, our smartwatch, or even the control unit of a car, depends heavily on how data is stored, shifted, and counted. And that's exactly why shift registers comes to play. They are the silent heroes that sit between memory and logic, managing how data moves around inside a circuit. Without them, we wouldn't have serial communication, proper timing control, or even smooth display operations. So, in this presentation, we'll understand what exactly shift registers are, the different types of them, how they can be configured as counters like ring and Johnson counters, their use in data conversion, timing, and sequence generation, how these simple circuits are actually powering the modern digital world. By the end, we'll realize that shift registers are not just theoretical, they are one of the most practical building blocks of digital design. So, now, what are shift registers? So, let's begin with the basics. A shift register is a sequential logical circuit. That means its output depends not just on the current input but also on the past history of inputs. It is made up of flip-flops, typically D flip-flops, connected in series, where each flip-flop stores a single bit of data. When we apply a clock pulse, the stored bit in each flip-flop shifts one position to the next. In simpler terms, think of it like a line of people passing a ball. Each time a whistle blows, each person passes the ball to the next person. That's exactly how bits of data move in a shift register. Now, based on how data is entered and taken out, shift registers are of different types. CISO, serial in, serial out. Here, data enters one bit at a time and exits one bit at a time. It's simple but slow. Used where speed isn't the priority, like basic delay lines. Next is SIPO, serial in, parallel out. Data is entered serially, but we can access all bits together in parallel at the output. This is very common in display drivers where we load data bit by bit but display all outputs together. Next one, PISO, parallel in, serial out. Opposite of SIPO, multiple bits are loaded simultaneously and then transmitted one bit at a time. This is useful in communication systems to reduce the number of transmission lines. There are also bidirectional shift registers where data can shift left or right depending on control signals used in counter and arithmetic operations. So in essence, a shift registers act as both a memory and a data movable unit, allowing flexible control of data flow in digital systems. Now, shift register as counters. Now let's move a step ahead. What happens when we configure this shift register to behave like counters? Normally, counters use combinational logic and flip-flops to move through binary sequence like 000, 001, 010, and so on. But when we use shift registers as counters, they generate special patterns of logical sequence that are extremely predictable and repetitive, perfect for timing and control systems. The two most common shift register counters are ring counter and Johnson counter. Let's start with the ring counter. Imagine we have four flip-flops connected in a loop. If we load the first one with a 1 and all others with 0, the single 1 will keep circulating with each clock pulse like a glowing light moving around in a ring. This creates repetitive pattern of states. For a 4-bit ring counter, the states will be 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1 and 1 0 0 0. Now, the Johnson counter, also known as twisted ring counter, is slightly different. Instead of feeding the output directly back, we feed the inverted output of the last flip-flop into the first. This doubles the number of states. For example, a 4-bit Johnson counter generates 8 states instead of 4. 0000, 1000, 1100, 1110, 1111, 0111, 0011, 0001, and then back to 4 times 0. So, Johnson counters are more efficient because they give more states using the same number of flip-flops. Now, moving to ring counter operating principles. Let's now understand how a ring counter actually works internally. A ring counter is made up of ND-type flip-flops connected in series. The output of the last flip-flop is directly connected to the input of the first one, forming a closed loop. Before the operation begins, we need to initialize the counter by loading one of the flip-flops with logic 1 and all other with logic 0. After this, each time the clock pulses, thus one shift to the next flip-flop moving in a circular pattern. Let's take a simple example of a 3-bit ring counter. We have flip-flops FF0, FF1 and FF2. If we start with the state 001, the next state will be 010, 100 and back to 001. The cycle repeats indefinitely. In short, a ring counter is like a revolving light system, one light on at a time, moving in a circle with each clock pulse.
Hello everyone, my name is Tanishq Patil and I will be talking about Johnson counter, data conversion applications and timing and sequence generation. So let us start with Johnson counter extended sequences. The Johnson counter, also known as a twisted ring or switch tail counter, modifies the feedback mechanism slightly. It feeds the inverted output of the last flip-flop back into the first. This causes a stream of ones to fill the register, followed by a stream of zeros, creating a unique pattern of states. For example, a 3-bit Johnson counter produces 6 distinct states in one full cycle. So compared to the ring counter, Johnson counters effectively double the number of usable states with the same number of flip-flops, making them more efficient in designs like frequency dividers and digital controllers. Data conversion applications. Shift registers are extremely important in data conversion systems. First, in parallel to serial conversion, a parallel in serial out PISO register takes multiple parallel inputs like an 8-bit data word and converts them into a serial stream. This is crucial in reducing wiring complexity and enabling long distance communication. On the other hand, serial to parallel conversion using serial in parallel out SIPO registers does the reverse. It receives serial data, reconstructs it into parallel form and sends it to devices like microcontrollers or DACs that operate on multiple bits simultaneously. In short, shift registers act as bridges between serial and parallel systems, simplifying circuit design and communication. Timing and sequence generation. Shift register counters like ring and Johnson counters are widely used for timing and sequence generation. Their predictable state transitions make them perfect for repetitive control systems. For example, in digital clocks, they can act as frequency dividers or phase generators. A 4-bit ring counter can divide a clock frequency by 4, generating a clean square wave. In multiplexers and demultiplexers, these counters can provide select lines that control which input or output channel is active at any given time. Thus, they are the backbone for timing, synchronization, and digital signal routing.
I'm Aarush Nair, and today I'll be talking about the industrial and consumer applications, the key advantages, and the references of shift registers. Now, let's look at where shift register counters are actually used around us. In appliance control systems like washing machines or air conditioners, they drive stepper motors and manage precise cycle timing. In display interfaces, shift registers control LED drivers and scan keypads efficiently, and it also reduces the wiring and cost. In safety systems like fire alarms and medical equipment, they handle monitoring and sequencing indicators. So, from household gadgets to complex industrial machines, shift registers quietly make everything work smoothly and in sync. Now, coming to the key advantages part, shift register counters have several clear advantages. The first advantage is simplicity. They require fewer logic gates, and simpler PCB layouts. Second, cost effectiveness. Due to high integration, they lower hardware cost and material count. Third, microcontroller compatibility. They can easily be controlled using standard serial protocols like SPI. Fourth, easy expansion. Multiple registers can be daisy-chained to extend bit length with minimal wiring. These features make shift register counters one of the most scalable and designer-friendly components in digital electronics. The references. These are some of the standard references we've used. Textbooks like Cedra and Smith's Microelectronic Circuits, Mano and Silitti's Digital Design, and Floyd's Digital Fundamentals. These sources helped us understand both the theoretical and the practical aspects of shift registers and counters. Thank you for listening. That was our presentation on shift register counters and their applications. We hope you now have a clearer picture of how these circuits store, move, and sequence data powering everything from small electronics to industrial automation. Thank you.